Welcome to a probabilistic filter comparison using the nuScenes dataset provided by Aptiv. This analysis was developed by the Ford Team No. 1 for the University of Michigan Mobile Robotics course. Combining localization and mapping research with automotive applications led to the selection of this nuScenes dataset for our project. Its environments, as shown in the example scene number 249 from the Boston Seaport area, provided multiple, varying real-world conditions to challenge the posed localization algorithms. We compared the results from using GPS and IMU data in an invariant extended Kalman filter with using LiDAR, camera, and semantic landmark data in a particle filter.
The invariant extended Kalman filter is relatively new, novel, and combines concepts from the normal EECF and Lie algebra. The aligned IMU and GPS data were used for prediction and correction. We predicted twice with the IMU at 100 Hz and corrected once with the GPS at 50 Hz. As you can see in this video, the performance of the IEKF does very well. The estimated pose lines up very well with the GPS ground truth, and the Cartesian covariance remains very small. The estimated yaw angle from the filter is pretty spot on as well. This is amazing.
The other method we use to solve the pose estimation problem is with a particle filter. Our particle filter uses semantic landmarks identified using cameras and LiDAR to help determine the vehicle's location. We use 100 particles and move using a random walk motion model and resample whenever the number of efficient particles drops below a set threshold to reduce the error. During initial runs of our particle filter, we found the total number of semantic landmarks in the scene was too high, causing a severe loss in particle location diversity. To ensure particle diversity and improve computational efficiency, we reduced the number of landmarks used to a variable percentage of the total available at any given time. As you can see, the resulting particle filter stayed close to the ground truth pose, but may need more refinement if it is to be used on a real-life autonomous vehicle.
Based on our results, we can conclude that invariant EECF performed near perfectly. However, the filter is extremely sensitive to GPS data loss and performs poorly if GPS data is unavailable for extended periods of time. In comparison, the particle filter had slight deviations from the ground truth and was sensitive to detecting too many landmarks, increasing the number of sample particles or motion noise while decreasing the number of landmark observations led to better results. In summary, invariant EECF performed significantly better than the particle filter, however, also proved to be more sensitive to a single point failure. For future work, the team will explore integrating multiple existing onboard sensors, such as the wheel speed and steering angle sensors, to improve the invariant EECF filter prediction to address sensor loss failures. In addition, to gain further confidence in the filter results, the team will include Mahalanobis distance calculations in the next experiment.
Thank you, Professor and Peter. We really appreciate it.